Page 58 talks about the domain and range, the fact that f goes from a set which represents this domain to its range, f inverse goes back the other way. F of A equals B, then f of B equals A. Do you see that particular statement on page 58?
Yes.
If f of A equals B, then f of B equals A. What's wrong with that statement? Yes, instead of, how should it read? If f of A equals B, then f inverse of B equals A, right? And so that statement is meant to be, if f of A equals B, then f inverse of B equals A. Notice the statement is the domain of f is the range of f inverse, and the range of f is the domain of f inverse. The roles of domain and range are reversed if you consider the inverse. Exercise 9 is a straight line, so it's just like the example that I did. Exercise 9 is let y equal 5x plus 3. What is the inverse for y equals 5x plus 3? Here is how a problem of this type could occur on this exam in multiple choice format. Matter of fact, I don't think they use y. So if f of x equals this, then f inverse of x equals a, b, c, all along, right? Got to pick it out from a list. So picking it out from a list, how do we go about it? Remember, it's really two steps. Y equals 5x plus 3. The first step is to solve for x in terms of y. So good. X equals 5x equals y minus 3. X equals 1/5 times y minus 3. That's step 1. Step 2 is reverse the roles of y and x. So we write x as the independent variable as we do for most functions. And so then you, instead of x and y, you write y equals 1/5 x minus 3. Then down this list you might have 1/5 x minus 3/5. And you're asked to pick out the inverse of this expression. This is how you'd go about doing it. Of course, the way we constructed it, this is the right answer. Huh? Can you repeat?
Why switch the x to y?
Yeah. It's perfect. We go through this construction because that's how the inverse is determined. If xy is a point on the graph of f, then yx is a point on the graph of its inverse. And yx just simply refers to the first entry, which comes from the domain, the second entry, which comes from the range. We almost never write x as a function of y. We almost always write y as a function of x. So we find out what the function is by solving for x in terms of y, but almost always write it this way. Okay? Can you do that? Yeah.
So you don't take your y, you don't take your x equals 1/5 times y minus 3 and replace 5x with that? See what I'm saying? So you have a value, you have now created a value for x, which is 1/5 y times y minus 3. You don't take that and put it back into the f of x equals 5x plus 3?
If you do, then you'll notice, because it is the inverse, if you take this particular expression and put it in here, then f of x just comes back to x. That is a property of the function and its inverse. Here, though, what you're trying to do is, given this function f, can you recognize its inverse? Which you'll have a series of functions here. What you want to do then under these circumstances is take the expression for the function, the original one, set it equal to y, even if it was written as f of x equals. Solve for x in terms of y, then replace y by f of x, or replace x by y or f of x, and y by x to write it in the usual function expression here. So, yes, if you then take this and compose the two functions, you'll come back to x. That's how it's constructed. But this is asking you to recognize the inverse. So, that's number 9. Number 10. Let's find the inverse of the square root of x minus 4. Well, let's make life a little easier for you. Let's look at f of x equals the square root of x. I want to find its inverse. Well, let's put a couple of points on this graph. If x equals 0, the square root of x equals 0. If x equals 1, then the square root of 1 is 1. If x equals 4, then this is up at 2, and so x equals 1, x equals 2. If x equals, that's at x, sorry, I put it in the wrong place. If x equals 4, it's up, darn it. That is what I meant to say wrong. If x equals 1, this is up at 1. If x equals 4, it's up at 2. Right, and the picture for this looks like the following. This is what y equals the square root of x looks like. So that if I draw the line y equals x, and then reflect this graph across the axis, like so. Notice so that each point here, here's the original function. You come down to here, continue on through, and then at each one of these points, these two distances are the same, right? So this is taking the original graph and reflecting it across the x-axis. This is the graph of f inverse of x. Given f, reflect its graph across the line y equals x to get a graph of f inverse. This looks suspiciously like part of a parabola, right? So, like before, let's proceed. Y equals the square root of x. Square both sides. Right? Y squared equals x. Okay? So here we've already solved for x in terms of y. Once we square both sides, reverse the roles of y and x. And here is f inverse of x, y equals x squared, just like this picture suggested. However, there is a little bit more to this problem because f of x, which is the square root of x, has domain.
All numbers.
No.
Oh, no, the other one.
Has domain.
All negative.
All x greater than or equal to 0. Range. Notice that there is an implied positive sign which sits in front of this. So this range is all y greater than or equal to 0, or all non-negative y in this choice. So when we form the inverse function, it reverses these rules. These two sets happen to be the same this time. All greater than or equal to 0x, greater than or equal to 0y. And you'll notice you don't get the full parabola. You just get that portion of the parabola which exists for x greater than or equal to 0. If you take f inverse of x equals x squared and compose it with the original function, the square root of x, either f inverse of x or f of f inverse of x, either way you do it, x goes to x. It's left fixed. Okay? All right. You need more of an explanation for that, or you feel pretty good about it. All right, so let's stop here today. Come on up and ask me a couple of questions about that. If you're unclear, I'll bounce back afterwards.